So what's the next bright idea we have? Well, you saw the pun I made there, bright idea. We're brightening things, right? So this is the map of approximate color of the Earth, as you can see. So here lighter colors obviously have high albedo, so you have vegetation which has a much lower albedo, desert has a higher albedo, and so on and so forth. Ocean, actually the glint depends on the angle of the sun, but you have to look at the average. So on average ocean is a pretty dark place, and the idea is, can we brighten the ocean surface, since it covers 70% of the Earth's surface. Obviously you've got a big lever if you can manipulate the ocean albedo. That's for just reflecting sunlight, but of course again we have to worry about unintended consequences. The data from satellites shows that over the period of at least the first decade of 2000s, the Earth's albedo is changing quite substantially. So this is the percentage change in reflectivity of the Earth. There are places where it's getting darker, and there are places where it's getting brighter. So the positive numbers here, bluish colors, are increased albedo, and the darker, obviously yellowish and so on colors are where there is a darkening. But this is, in a global sense, not a trend, even though there is some indication that maybe it stays above the long-term mean for some period and then oscillates, and maybe there is a trend, but this data has to be extended. So there are natural and anthropogenic causes now mixed in terms of increasing humidity, carbon dioxide, changing vegetation, urbanization, agricultural land, deforestation, etc., which are contributing to albedo changes. The idea of brightening the surface comes from this contrast we see here. The Arctic is a good candidate for brightening the ocean surface as well, if we just wanted to do a reflection to reduce warming of the Arctic. So you can see the contrast of sea ice and the open ocean, and how different the ocean albedos are. So obviously the much larger energy absorption here during the spring summer months over the Arctic are going to drive the ice melt pretty rapidly because of these albedo differences. This is the general idea. Chemicals could be added to a ship's wake to make it last longer. So the wake here is quite bright because of the micro bubbles that are produced, and all those clouds that were produced by the emissions from the ships can now be also seen as brightening the wake. So again, remembering the unintended consequences. The microbubbles, if they last longer and they reflect much more sunlight, what does it mean for the productivity of the region, the marine ecosystem of the region, the gas exchanges, oxygen, CO2, N2, etc., all have to be worried about. Nonetheless, we always are brave in trying our experiments. This is from a paper here posted on Harvard that used a model to, they actually did lab experiments with micro bubbles blowing to see how long it takes for the bubbles to rise and so on and so forth, and then they did this global scale experiment. I think the experiment was actually done by Ken Caldera and his team. This used the community atmospheric model from NCAR version 3.1, which is an older one. This is showing the temperature change in kelvins from global ocean albedo increase of just 0.05 with 780 ppm of CO2 doubling. So you go from whatever 390 or so to 780, and then you in the meantime increase the ocean albedo by 0.05. Sounds like a small number, but considering albedos are typically very small for the ocean. That's a fairly significant fraction. But the main point is that the dynamic impacts can be seen here. So you have cooling over here, which may be bad news. Cooling over here, which may be bad news. Sorry, yes. Okay, and there is these large-scale global impacts. Overall, in terms of the goal of cooling the Earth, obviously this works very well, but what is the impact of these coolings on the circulation, on crop yields, on health, and so on and so forth, or generation of hurricanes, for example? That's a massive cooling here of 7 point, almost 5. Let's see here, this is pretty small. This is in the range of 1 Kelvin or so. So there are some large numbers locally, but mostly it's in the range of, let's say, 1 Kelvin, which is not insignificant in terms of energy balance. Okay, so that's the main point. The final point we want to make is that these kind of experiments are dependent on which hemisphere you do in, and you can learn that also from natural experiments. For example, when volcanoes went off in the northern hemisphere, the Sahara rainfall was severely negatively impacted by the cooling and the aerosol loads and so on. So if the geoengineering is done in the northern hemisphere, then we end up affecting the large-scale patterns of rainfall in this way. You have increased the rainfall here, but you have decreased it severely over the ocean here and also over this sensitive region of Sahel and Sahara. Whereas if you do the geoengineering experiment on large scale in terms of, let's say, aerosol injection in the stratosphere, then you are going to increase rainfall in the northern hemisphere and decrease it in the southern hemisphere. So it's not just the impacts, but it is the hemispheric asymmetry of the impacts that we have to worry about. So how does that come about? I missed, here it is. How did I jump that one? Okay, so there is something called the Intertropical Convergence Zone, which you can see here is a cloud band. There are all sorts of clouds everywhere, but this is the permanent rain band in the tropics where the northeast trades and the southeast trades converge. This band moves back and forth with the sun and so on, and over the Indian Ocean it breaks up because of this monsoonal circulation we have, which is from the southwest into the northeast in the summer months, boreal summer months, from the northeast to the southwest in the boreal winter months, and so on. So when you do radiation perturbation either in this hemisphere or this hemisphere, you're going to move the so-called intertropical convergence zone, and that's why you're going to end up with these patterns. So the convergence zone is right there. If you move it to the south, you're going to strengthen the winds here and weaken them over there, weaken the rainfall here, strengthen the rainfall here, and vice versa. Okay, so again, brightening the ocean with microbubbles or adding chemicals to the ship's wake is an idea that is considered, and the ocean does provide a very large surface over which small albedo changes can make huge changes in the energy budget by reflecting sunlight, but the unintended consequences remain to be fully figured out and worried about, not only on land in remote places but also locally in the ocean in terms of the marine ecosystem and other biogeochemical processes. Okay.